All right, so in the previous video, we talked about calculating total resistance in a series circuit. We talked about how a series circuit means there's only one path of current to flow. We know that because of a series circuit, current will be equal at all points. So notice the current flowing at all points. So we determined the total resistance, and using the voltage and the total resistance, we calculated the total current. And then we did the voltage drop looking at the total current times the resistance value of that individual resistor, and we get the voltage drop at each point. We also know, we mentioned in the last video, that Kirchhoff's law, voltage law, states that the sum of the voltage drops will be equal to the source voltage in a series circuit. So we had a 24 volt source, so VS voltage source, and then the voltage drop across R1, the voltage drop across R2, the voltage drop across R3, the voltage drop across R4, and the voltage drop across R5. If we add those numbers up, these sum together to equal 24 volts. Now the law actually states that the sum of all, being these would be negative and this would be positive, would be zero, but that basically means the voltage source and the sum of the voltage drops has to be equal. So that's how we got to this point. So what I want to talk about now is the power consumption of each resistor. So the power equation, there's a nice diagram that we use for this one too. The power equation of Watt's law states that the power consumed is equal to the voltage times the current. So in this case, power, which is units or watts, is going to be equal to voltage times the current. So P is going to be equal to V times I. So in this case, we know the current. We solved for that earlier. And we know the voltage drop at that point. So we're still focused on the one resistor, not the whole circuit with the single resistor. So what we're looking for now is the power consumption of resistor 1. So we're going to call this P at 1. So if we look at this law, voltage, we're going to call this the voltage drop. So I'm going to rewrite this in reference to this individual resistor. So the power at R1 is going to be equal to the voltage drop of R1 times the total current. The total current we already knew here. The voltage drop we calculated in the previous video, and now we're going to determine how many watts of power that individual resistor is pulling. So if we look at this equation, we have the power consumed by R1, the power consumed by resistor 1, is going to be equal to the voltage drop at R1 times the total current in the circuit. So in this case, if we plug in the numbers, the original voltage drop was 2.08, and the total current, which is 0.0208. This is the decimal form, and this is the metric prefix. So milli meaning -10 to the -3. Remember, always use the base units. You have to be in volts and in amps in order to get the correct units. If you forget to do that, you'll be off by 1,000 or 100,000, so on and so forth. So if we have a 2.08 voltage drop times a 0.0208 current, then the power consumed by this resistor is going to be 0.0432. And if we move this over, that's going to be 43.2 milliwatts. So power is in watts, that's the W. We move the decimal 3 times back, it's a smaller number, so this is going to be 43.2 milliwatts. So the power consumed by this individual resistor is 43.2 milliwatts. So remember, we're looking at only this resistor, so just focusing on the values right here. We had a 100 ohm resistor, we had a total current of 20.8 milliamps, and then based on those we figured out a voltage drop of 2.8 2.08 volts. To do power, I simply need the voltage times the current. Then what we're going to do is the voltage drop at this point times the current flowing through this point, and this is the power consumption of this resistor. We can continue and do this continuing on. So we're going to look at the power consumed by resistor 2. We're going to do the same numbers here. We're going to look at the voltage drop, 3.2. We're going to multiply that by the total current, which is the same at any given point. We're going to get 64.8 or 64.9. Comes out to 0.06489. So we're going to say 1, 2, 3. That is going to be 64 point, we're going to round up, 9 milliwatts consumed. That becomes the power consumption of resistor 2. We're going to repeat this for all 5 resistors. Same mathematical equation. We're just looking at the voltage drop times the total current. If we notice here, these two had the exact same resistance. They had the exact same voltage drop. It's the exact same current. So we already know at this point that the power consumed by R3 is going to be equal to 43.2 milliwatts. So we're going to skip on down. We're going to go to this one. So we have a voltage drop of 6.24 volts times the 0.0208 amps. And at this point, we're going to get 129 milliamps. So it comes out as 0.1297. That would be watts, or 100, and we're going to round that up to 30 milliwatts. So the power consumed by this resistor, so the power consumed by resistor 4 is going to be equal to 130 milliwatts. So the original number came out to this. So move the decimal back 3 times, we get 130 milliwatts. We'll repeat this for resistor 5. So the voltage drop there was 10.4, and the total current going through it again is still 0.0208. We'll multiply those together. So this is total current times the voltage drop. And we get 216.3 milliwatts. So it came out to 0.2163 watts. And if we convert this to metric format, it is 216.3 milliwatts. That is the power consumption of resistor 5. 216.3 milliwatts. So in that way, we originally had 24 volts. We had the resistor value of every resistor. We determined the total resistance, or the sum of all the